Good evening. Welcome to this 7th class of analytical chemistry, where we are discussing about the role of analytical chemistry in different spheres of life. So, what we are talking about is the role as well as the different techniques, what we can use and what we can follow, particularly the apparatus. Because the most important thing always we know that what are the apparatus we can use to follow some analysis, because this particular thing what we are talking about, the analytical chemistry and the laboratory techniques. So, these laboratory techniques are very much dependent on the apparatus what will be used. So, that is why this apparatus is related to the techniques, where we know that a typical chemical analysis, when a technician can perform, he is relying on this particular techniques and the handling of so many apparatus for that particular technique. So, slowly we will see that how these tools, the different techniques and the chemicals are important. Suppose we are analyzing some ore. So, suppose some ore material. So, very first thing is that our problem we know that is a ore material we have to analyze for say its iron content. So, what are the things we can use or what are the things we can apply for that, starting from the different tools to the chemicals. So, these are very abstract definitions for the time being to you, but what you can feel is that definitely when we do for something where the tools are very simple tools, we all know that a burette, we all know what is the burette and how the burette is also useful with the pipette. So, these are the very simple tools. We are not going for talking about the complicated instruments where the instrumental techniques are available. So, those instrumental techniques are also giving us something related to those tools. So, a burette and pipette can be your tool, and what are the chemicals we can use? That means the ore, and the next immediate problem to that ore is the dissolution. How we can dissolve this ore into some solution such that ultimately what we can have the solution where the analytes are present and we can analyze that particular solution for its iron content. So, we are talking about so many things, because this ore, if this is coming from some mining process or it can be obtained from the different rock sample, as I told you earlier, from the earth surface or from the Mars surface or any other surfaces what we can get these. So, the physical characteristics of these ores what we are talking about is also important, where we can reduce the size of these solid sample to a powder form. So, the useful form what we can use for the treatment of the different chemicals for its dissolution is also dependent, because if you have a big size of ore which we cannot put inside the some mineral acid such that it can be solubilized. So, what we see is that if we have a solid for the processing of the sample, so these we already discussed little bit. So, if we have the solid sample, so we can crush it, we can pulverize it and grind it. So, these three processes for processing of the sample give rise to the powder material which we can ultimately analyze for its content of the analyte. If we have the liquid what you can do, the liquid, if we have the solvent, evaporation can take place, leading to change in concentration. So, if we have a liquid of large volume, and therefore, the concentration of this iron such that you have the powder sample of that ore and we make it powder, and then the powder is dissolving in the acid. So, we are dissolving in that particular acid, and after that if the solubility or the dissolution process is not so easy and we get a very large volume. So, immediately what we can do, we can reduce the volume of any liquid sample. So, for liquid sample it is very easy to tell that a large volume can be concentrated such that we can increase the concentration, that means the percentage of iron in the solution can be increased. For the gas sample, what we see, that to prevent contamination by atmospheric gases, that means we will not use something where the atmospheric gases will come and contaminate the gas sample what we are going to analyze, such that we are going to analyze nitrogen, and if the nitrogen is contaminated by the oxygen of the air as well as the nitrogen of the air, then our process will be a difficult one, our estimation will be erroneous. Then to dissolve all these things, an ideal solvent should be chosen to dissolve all the sample including the analytes. So, what we can see that these, including these analytes, that acid can be your solvent, what we can consider it, but if it is some organic matter, some organic solvent we can use to dissolve these analytes. And if we have some insoluble material, so which will require some chemical treatment, that means we will discuss afterwards that for some insoluble material, we know that for a typical analytical process, the inorganic sample, if we can have, which is insoluble. What does it mean? That insoluble inorganic sample, that is not soluble in the aqueous medium, it is not soluble in water medium, even after if we treat with it by the mineral acid. That means, if we have the sample containing oxides or sulfides or nitrates or sulfates, this is not going to the solution. So, we can go for something which we will discuss afterwards, that we can go for fusion. A high temperature fusion can be useful. When we go for this fusion, what we get? We get a melt. That means a fused sample, which is nothing but your fused this insoluble inorganic sample. So, if we have the fused sample which we get as the melt, and now if we add pure water, that means acid free water or some alkali or some mineral acid, we get, there is every chance of getting a solution out of that particular melt. We all know that at this point of time we can give you some example, that is a mineral of manganese, which is MnO2, which is a black powder, is pyrolusite, and the solubility of this pyrolusite in acid is not good, even in water it is completely insoluble. So, we can follow this particular process, you can fuse it, and if you go for the alkali fusion, that means sodium carbonate and sodium hydroxide or potassium hydroxide on some mica foil at a high temperature on the Bunsen burner or any other open flame, what we get is that this can be converted to some melt. And what is that particular melt? Melt is coming out from MnO2 due to this oxidation, and it can give rise to MnO4 2 minus or MnO4 minus. That means, it can be fused to manganate or permanganate anions, because the corresponding cations which are sodium or potassium depending upon the use of potassium hydroxide or sodium hydroxide during the fusion process, we get either sodium manganate or sodium permanganate or potassium manganate or potassium permanganate as the melt. So, the chemical treatment, that is why, is very important. So, insoluble samples might require, because we have to be very much careful whether the sample is purely insoluble. So, we take the advantage of this chemical treatment, and this chemical treatment in this particular case is nothing but the fusion treatment to convert the analyte into the soluble form, where we can solubilize this particular analyte into the solution. So, what we see that analysis on replicate samples and the results are averaged. So, we can go for 1, 2, 3 or 4 samples. So, 4 samples can be analyzed together, and we take the average of it, which is acceptable range of the corresponding percentage of either manganese or iron in this particular example of ore. Then several other important steps we can follow for this particular analysis, where we see that how the other important steps we can follow for this particular analysis, where we have interference. So, if we have this manganese dioxide, that means the pyrolusite as the ore, in this manganese dioxide, which is a black powder, and depending upon its source, that means where from it is coming, that means which mine is giving this particular pyrolusite, we get this as the black powder. But what is the percentage of MnO2, that means the pure MnO2, that we do not know. So, it can have charcoal, it can have other black material inside. So, how to eliminate the interference such that we can go for enrichment. So, that is the typical process. Enrichment is, that means we want to increase the corresponding concentration of manganese dioxide in pyrolusite. So, the typical enrichment can also give rise something that, depending upon this percentage of MnO2 compared to the percentage of, say, some charcoal. Some charcoal is also present along with this manganese dioxide as pyrolusite. So, this particular enrichment process, if we can follow, we can increase the concentration of pure MnO2 in this particular material, such that we eliminate the interferences of some other extraneous matter. Then we can go for calibration for a particular type of measurement. So, calibration and measurement both will go side by side, where a particular technique can be calibrated. That means, we can take some known sample of manganese, known sample of pyrolusite, which can be a certified sample, which we can analyze by this particular technique, and the concentration can be tagged with the unknown sample what we are measuring. And finally, we get the results for the different calculations, and ultimately we can evaluate the corresponding technique, how good this particular technique is to go for the corresponding analysis of the sample. Then one particular thing we can follow now is the evaporation. So, evaporation is a very simple and useful technique, because we were discussing about the different techniques. So, if we consider a very simple thing, that means which is your evaporation. So, how you will define and how will you go for the evaporation? Just now we are talking about a very dilute solution of any sample which contains say Fe3 plus. So, a ferric solution, a ferric ion solution is there. So, this ferric ion solution in a large volume of water. So, volume of water is very large. So, we have to reduce the water content. how we can do? Because we all know that if we want to remove this water, it is a simple process of evaporation. So, how to do that evaporation? So, this is there, say suppose this particular ferric solution is there in a volumetric flux. And we know that volumetric fluxes are coming of different volumes, say 100 milliliter, 250 milliliter, 500 milliliter, or a liter or 2 liters, etc. So, from this volumetric flux we can have some volume of this solution. Suppose we are having some 250 milliliter of this ferric solution, and the concentration of this ferric present in this particular flux is very less. So, we can go for evaporation. So, how to evaporate that? So, that is the next question what we can ask, that how to evaporate this particular solution such that there will be very rapid and quick evaporation of the water molecules from the solution. So, we cannot do. So, we all know that a very simple volumetric flux has a shape of this type, so which is graduated. So, we can have this volumetric flux. So, what is this? This is the mouth, and the mouth is very small, and we cannot heat the volumetric flux because we can damage the volumetric flux if we heat it. So, what we can do, we just transfer this to a beaker where the mouth is large. So, we just transfer the whole solution of this 250 milliliter in a beaker. So, we have the beaker, then we put this on over a Bunsen flame and we go for the evaporation. So, what will happen, that evaporation can take place, and as this volume is reducing and your Fe3 plus concentration is increasing, what to do, that we have to be very much careful that this open beaker may not be very much useful when the volume is reduced to a small amount. So, what we can do this evaporation process by doing this. So, taking the help of this beaker with a glass rod, and this we can put on the Bunsen burner and we cover it with a lid. So, is a typical lid of glass. So, we consider this as the corresponding lid of glass and cover it such that you have this vacant site on these, particularly this tip side where the rod is being inserted, and we keep on heating this solution. So, solution original volume was say up to this point, say, and is reducing, and we can reduce further, and during this process through the sides when the volume is less, if we keep on evaporating this from this solution, that this vapor, water vapors will come out from the side of this lid, the glass lid, and the corresponding thing, that means if we do not allow its open evaporation, is covered with a lid, and therefore, the evaporation rate is restricted, and some of the water vapor is coming and touching this lid and is getting condensed and will go back to the solution again. So, the rate of evaporation when it is covered is less. So, initially when it was open, the rate of evaporation was very high and a very fast reduction of this volume was taking place, but remember that the concentration of ferric ion was also less, but when the concentration is increasing, we should be very much careful in covering the solution and we should allow slow evaporation. So, the rate of evaporation is being reduced, but one important thing, one difficult thing can happen at this particular point, that since the solution is getting concentrated. So, when we are handling a concentrated solution, and in the concentrated solution what can happen, that local heating can take place, and if there is a sudden and violent boiling, that tends to spatter solution out of the container, that is known as bumping. So, at this point bumping can take place such that this, because what is going out from the solution is the dissolved air or the dissolved oxygen as bubbles. So, after some times the amount of dissolved oxygen or air is less, and if this glass rod is not sufficient to allow the escape of these vapors, that means the water or air vapors by the side of this glass rod, what can happen? There is the local heating can take place over here, and this water vapor from here can go out as bumping the solution. So, when this is bumping, it can take out some of the solution out of the beaker. So, we will be losing some of the solution. So, care should be taken to avoid that particular type of bumping, such that no such solution or even a single drop of solution can go out from the beaker, which will reduce the actual concentration of the solution. So, this particular process, because everything is related, because we are talking about the dissolution, and after that, that means when we talk about the dissolution of any ore, we can have something which is also related to evaporation for a process, that means the dissolution process or some acing process. This we have seen in of any one of our previous class, where we are talking about the arsenic poisoning of the deer family, where we are going for some acing process which we termed as the dry acing, because whatever arsenic present over there has been converted to arsenic pentoxide as the corresponding oxide on a crucible. So, heating any sample and forming the corresponding oxides by heating in air or plenty oxygen of that air, giving rise to the corresponding oxides, is known as the corresponding dry acing process. So, acing is such that we are getting the different assays. Sometimes assays are not containing any active ingredient, that means active these oxides and all these, because it can so happen that we will see that you can get Fe2O3 or Fe3O4 from the solution of Fe3 plus. So, this is a typical process where we can go for a dry acing of Fe3 plus solution, what we are just seeing for our beaker evaporation, open beaker evaporation of a solution containing Fe3 plus. But ultimately we can convert these as the corresponding Fe3O4 or Fe3O4 for the acing process. Now we will see, so these acing processes can be of two types. So, this what we discussed earlier is the dry acing process. Now we will see something which is that wet acing process. Acing process is wet, what we are talking about. Dry is fine, we get some white powder, it may or may not contain some oxides of arsenic or any other material. It is simply some ash. So, carbon, when we burn carbon, the coal we burn, we all know that some ashes are forming, that means those ashes can have some oxides of the material what is coming out from the coal. But what about this wet acing? Because it is not going with that language that acing we are doing for the acing with the wet. That means we are doing something or we will be doing something such that we can go some destruction of some part of the material to go some ash, and that ash can be taken into the solution. So, one such example is our wet acing. This wet acing is nothing but if we have some organic constituent in your material what we are handling. So, what we can do, we have to oxidize that particular organic material, because the organic material we all know is forming from carbon, hydrogen and oxygen, and if we are able to oxidize by nitric acid, it can be converted to carbon dioxide and water. So, this particular thing, when we know that initially what we can get if we treat it with acid, sometimes we treat with concentrated sulfuric acid. So, we all know that from our school days example, that sugar we all know if that sugar is treated with concentrated sulfuric acid, we know that we are leaving behind with carbon, the charcoal type carbon we are leaving behind. So, that is a black material. So, that black material is leaving behind, and that black material, if we are not able to treat it, so this carbon from sugar, this carbon can come also from some organic molecule. So, from that organic molecule, if this carbon is coming out as black particles, so we cannot have these black particles inside a solution. So, within the solution, the entire solution will be black in color with floating carbon particles and will be contaminated by all these carbon particles. But in a regular fashion or in a slow way, if we oxidize this particular carbonious matter or any organic sample by addition of sulfuric acid or nitric acid, we can oxidize this carbon without forming this carbon as the carbon particle. We can convert this as the carbon dioxide, and those carbon dioxide can escape from the medium. So, we can take not only concentrated sulfuric acid, we can take nitric acid, we can have sulfuric acid, all are oxidizing agent, then hydrogen peroxide, aqueous bromine, and sometimes the combination of these, because we do not know what are the species will be useful for destroying any such organic matter for this particular oxidation process. So, one such example we can take, as we will be talking afterwards once again, that if we are going for the analysis of Ni2 plus, and this Ni2 plus can be complexed with some reagent which is dimethyl glyoxime, which is abbreviated as DMGH2, and that DMGH2 when we use is forming a complex of stoichiometry NiL2. One nickel is bound to L2, we know these are known as coordination complex. So, what it has? So, we are talking about something that how we can analyze the concentration of nickel in a solution, which is like this iron solution is unknown solution of nickel. What we can do? We can use this organic molecule, that is your reagent, that is organic chelating agent. We call it as the DMG as the organic chelating agent, which bind nicely with NiCl2 salt or Ni2 plus to give this, and this is a corresponding pink red precipitate coming out from the solution, which is insoluble in water. So, this can give rise to several opportunities for analysis of nickel by this particular technique. So, this we will discuss that how we can use by taking the weight of this nickel salt of nickel complex of DMG by gravimetric estimation. If we are able to solubilize these in some organic solvent, we can go for some spectrometric method of analysis of nickel. But for this example, that how we can get back this nickel 2 plus in aqueous solution from the NiL2 complex, how to get back, like the getting the corresponding iron ion or any other metal ion from the ore sample. So, this is also another example how we get the nickel ion from this NiL2 species, which is a coordination complex. So, there basically we can destroy the organic part, we should be able to destroy this organic part by treating this nickel DMG complex by mixed acid of concentrated sulfuric and concentrated nitric acid to oxidize it. That means, this organic molecule, the DMGH2, when it is bound to NiL2, it is the form which is DMG. One proton is lost, so it is one negatively charged, which is balancing the corresponding dipositive charge of the nickel. So, you have to destroy this entire DMG sample by treating with those combination of acids to oxidize it for CO2 and H2O. And in that particular way, what we get? We just get this in the aqueous solution. Carbon dioxide will be present in the solvent medium, that means the aqueous medium, and ultimately it will escape out from the medium. But what we can have now in the solution, within the solution we get Ni2 plus in that particular solution. So, this is a typical example of wet acing, how we destroy the ligand which is bound to our nickel 2 plus, and how we can handle this particular thing for analysis back. So, this is the technique. So, these two are all interrelated to this particular analysis, that we have Ni2 plus, and that Ni2 plus we are trying to bind it with some organic reagent and we get this, and once it is formed. So, this is a particular composition or a definite sample of metal ion complex of nickel 2 plus, which we can analyze by two different techniques. One is the gravimetric technique and another is the volumetric technique. But at the same time, the process of this wet acing, what we are talking about, this wet acing inside a beaker, because we can take the sample of this nickel DMG inside this beaker and we can destroy the organic part, that means the DMG part, by treating it with a mixed combination of this nitric acid and sulfuric acid, and we will be leaving behind with Ni2 plus. So, this is also true for any general example of metal complex. This can be any of these metal ions, it can be Al3 plus also, and this can be any useful ligand which binds to this metal ion to give you this corresponding complex. So, this wet acing process is always we can follow, that we get the corresponding metal complex and we destroy the metal complex. So, this is the destruction process, the acing process. So, wet acing process is the destruction of the corresponding ligand part, and if we destroy the ligand part in the aqueous solution, we will again have the corresponding metal ion, that means aluminum 3 plus in the solution. So, this is a particular technique how we get this from, say, some aluminum ore also, which is your bauxite. So, something we can get as the aluminum 3 plus, which can be complexed with some ligand, and again we can get back the aluminum 3 plus from this complex. Okay, thank you very much.